if problem has two-dimensional state space, often you can write it on a line. If it's an energy shell, you could be in 3 dimensions, but energy shell could be some curved surface of constant energy, which is 2-dimensional. Then it's really a manifold, so you cannot write it in a line when you do that. But often you can draw things in the plane. And then if you have a point, your law gives you a trajectory. It says where it came from. You can draw a line like that. And at every point, you have a tangent space, but because it's 2-dimensional flat space and you looking at 2 dimensions, in Strogat's book, it's overlaid on each other. So this vector field, you draw it on the same plane, even though they're different spaces. This is the manifold where your thing happens. And locally, there is a plane. At every point, there is a plane. So the tangent space is really amazingly complicated because every point has a vector space associated with it. And that's the true story. So when you draw these little vector fields, directions of where the vector field is, they don't live in the same space. They live in a separate space. And at every point, there is such a tangent plane. So that's an honest answer to a question. But in these 2-dimensional examples, when you can overlay them, and then it makes sense. It says, at every point, there is a 1-dimensional direction, which is direction of your vector field, and its length means how fast you move. And your integral, you think of it as in a plane, and you add up this little space steps at different velocity, you get a trajectory. So in a plane, you can think this way, but I don't like it. It's misleading. That's not what it is. The nonlinear problem always lives on some manifold, like this manifold here. At every point, there is a tangent space, which gives you instructions infinitesimally what to do. But that changes all the time. So as you go, this plane is, so they're really separate spaces, and it's very hard to, so they call it the tangent bundle. So what mathematicians, geometers mean by tangent bundle, they say it's a bundle of these linear spaces, which here is drawn as a plane, but in D dimensions it's some vector space, which is not a plane. And you have a bundle of those guys. You have infinitely many of those. At every point, there is a tangent plane. And that's how geometers think about geometry of smooth differentiable spaces. You can chart them, you can explore them by making little local maps of Alabama, Missouri. The official lecture is done. I'm open to inquisition. Or I'll go and get some sleep.